Good morning. I'm Zachary Knowles.
I'm Christian Tedeschi.
I'm Rashid Chung.
And our project is the aluminum airfoil car optimization. So just what is our project? It was adopted from the Rutgers Chemical Engineering Car Competition, or CHEMI car for short. And what happens is, participants must create a small car that can be powered by a chemical reaction. The car must start and stop on its own, and the goal is for it to travel between a specified distance between 50 feet and 100 feet, while carrying a variable load between 0 grams and 500 grams. An additional challenge is that the participants do not know exactly what the distance and weight will be until about an hour before the competition, so there must be a lot of testing to ensure they can get as close as possible to the specified distance. Our project involves many principles of physics, chemistry, and engineering. This is our actual car. Here's the battery that receives power from the fuel cell. They're not pictured here, but I'll show you them later. Here's the motor, which powers the wheels, obviously. And this is our stop mechanism, which I'll explain in a little bit. This is a diagram of our actual fuel cells, and I'll tell you how they work. This is an oxidation reduction reaction, and what happens in these reactions is that electrons are generated in the anode, and then transferred to the cathode. In this case, aluminum foil is the anode, and activated charcoal, which is carbon, is the cathode. And as electrons are transferred, this can create an electric current that can be used to generate power for our car. We wired a lot of these fuel cells together and created circuits with multiple fuel cells, and we connected it to a photoreceptor, which is related to a stop mechanism, which I'll explain right now.
Excuse me, could you use the mic? It's harder to hear you.
Can you hear me now?
Yeah.
Okay. Our stop mechanism, as shown here, we have a LED light that shines through the little tube that I showed you before, and you have a photoreceptor on the other side. And what happens is that the photoreceptor will sense when there's no light passing through this solution. This solution will turn dark after a certain amount of time. This is an iodine clock reaction. And what happens is that we added sodium metabisulfite, starch, and water into a solution, and eventually added potassium iodate, which will turn the solution black. We vary the amount of potassium iodate that we put in here, and we can vary the time that the solution will turn black. So we can control how long it takes until the car will actually stop. Because when the photoreceptor senses that there's no light passing through the solution, it will break the circuit of the starting mechanism and will stop power to the car completely.
So how do you make fuel cells? You take paper towels soaked in saline solution and place them on a similar sized aluminum foil. You then take activated carbon and sprinkle it on top. You then take a stripped copper wire, insert one into the fuel cell, fold the fuel cell over, and leave one outside. This outside one attaches to aluminum foil of another fuel cell. These fuel cells are then clamped together through the use of plastic pieces, are separated by the use of plastic pieces, and are put in a clamp. The clamp is used to produce a greater current, and this is the process of how we actually made the fuel cells. So the stopping mechanism, the iodine clock reaction. It is composed of three solutions: a starch solution, a sodium metabisulfite solution, and a potassium iodate solution. In order to create the starch solution, we had to first boil water before we could actually add the starch into the solution. Once we added the starch into the solution, we had to cool it down through the use of an ice bath. After we cooled it down to 25 degrees Celsius, we inserted starch solution, water, and sodium metabisulfite into little 100 milliliter beakers. These beakers would be used for this. These beakers would be where the stopping mechanism actually occurred. We took various volumes of potassium iodate and noted the differences of how long it took the solution to darken based on the differences in volume. This table here shows the left side is predominantly just single fuel cells, their amps and their currents. The amps and their voltage, I'm sorry. The voltage was approximately 0.75 volts per each cell, while the amps were about 0.5 for each cell. On the right, it is a combination of these fuel cells. They were wired in series. As you can see, the voltage increased, but the amps tended to stay the same. And this picture shows the actual cell, the fuel cells and clamps being wired together. They were all wired in series as to produce the maximum voltage possible. And this is a graph of that plots the volume of potassium iodate against the amount of time it took for the solution to completely darken. It is an exponential decay graph, which means the more potassium iodate you add into the solution, the quicker the solution darkens.
I hope you guys can hear me clearly.
Yes.
That's good. For the analysis, we use various methods to analyze the data we obtain in our experiments. First of which is Ohm's law, which basically states that voltage equals the product of current and resistance. We want to lower the resistance because when the resistance is low, current is very high. So we wanted to minimize the resistance. So what we concluded from this, from putting the cells in series and parallel and calculating all the total resistance, current, and voltage, we concluded that we had to wire the cells in series because in a series circuit, the voltage is added while the current stays fairly constant, and our cells lack in voltage while we had superfluous current. Also, we used various Newtonian physics equations, which basically describe moving projectiles in 2D motion. So we basically use distance equals rate times time, and the bottom equation is the main kinematic equation that can be that the top equation can be derived from. Why is this equation important? It was important because we found that acceleration was constant, and we were given the velocity, which is the rate, and the distance, so that we can find time. The time that was found was plugged into the graph Chris mentioned before, the iodine clock reaction graph, and we could find the appropriate amount of potassium iodate solution that was needed to execute the certain scenario in a successful fashion. Also, branching off of that, we use scatter plots and the line of best fit, and also a data table in order to view the data with more ease and make it more accessible. Also, we faced many struggles in the process of executing the experiments, and we solved it with our flexibility. For example, as Chris mentioned, we had to cool down the ice solution. The starch solution with ice, but unfortunately the ice machine broke, so yeah, we couldn't use ice. So we used what we call a beakerception. It's exactly what it is. It's a beaker inside a beaker inside a beaker, like dream inside a dream. Yeah. So the innermost beaker contained a starch solution that was needed to be cooled, and we put 2 beakers outside of it that contain cold water so that the starch solution can effectively cool. And we have some advice for the future experimenters who work to experiment with ChemiCar. First, we like to emphasize efficiency. Efficiency is a key to this experiment because a lot of the preparatory measures, such as making the fuel cells and making the iodine clock solutions, are very tedious, and you will lose a lot of time if you don't split up the work efficiently. And also, we have to the future experimenters must test some of the important factors we missed, such as the pH of the solution, because pH is very essential to electrochemistry, as it is the ratio of hydrogen ions in the solution. In conclusion, our project cost a total of $248.79, which was under the cost limitation of $300, so it was successful in that fashion. And we also concluded that aluminum foil batteries, airfoil batteries, although they're very easy to make, are really highly inefficient and impractical because the saline solution we used to make the fuel cells were dried out too quickly and made the battery dysfunctional. And even if the batteries were functional, the data it gave off were too fluctuating, and it was a big disadvantage for us. And through research, we found more alternate cells, such as copper sulfide batteries that lasted longer and gave off more stable data. Also, we learned more things about just general lab procedures, such as like recording the data properly. We used to scribble data just on a piece of paper. Now we know how to neatly construct a data table, plot, and organize them. We also learned that teamwork is vital for many experiments such as these, and the whole project as general, because we couldn't do it by ourselves, and we had to split up the work efficiently to fit all the work in this given amount of time. So for acknowledgments, we'd like to thank our project RTA Kristen Stevens and our project mentor Sumit Sikka, who is here somewhere, I can't find him in the audience, and Matthew Sowinski.
We would also like to thank Dean Eileen Rosen, Director of Governor School, and Jean-Patrick Antoine, Assistant Director, and we would also like to thank the Governor School Board of Overseers.
I'd also like to thank everyone who sponsored the GSET, making this opportunity possible, such as Rutgers University, the State of New Jersey, Morgan Stanley, Lockheed Martin, South Jersey Industries, and PSCG.